Welcome to a video that will introduce functions of two variables. The goals of the video are to determine function values of functions of two variables, and then also to determine the domain of a function of two variables. The function z equals f of xy is a function of two variables, so z is defined in terms of both x and y. Therefore, the domain is the set of all possible values of x and y. Again, x and y will be the inputs into the function, and z will be the output. So the range is a set of all possible values of z from the domain. And since the function contains three variables, x, y, and z, the graph is a set of all possible points called ordered triples, x, y, and z, that are produced by the function. And geometrically, the graph is a surface in space. So let's first start by taking a look at some cool graphs of functions in terms of two variables. Here we see z equals cosine x times sine y. Notice it produces a surface with hills and valleys. Z equals the natural log of 1 minus x minus y, produces this surface. Here we have z equals the square root of 4 minus x squared minus y squared. And then lastly we have z equals e to the power of 1 minus x squared minus y squared, which looks like a peak. Let's take a look at these in another way. Again, here's the graph of z equals cosine x times sine y. Here's the graph of z equals natural log of 1 minus x minus y. Now these graphs are done on Maple, and notice as this graph moves downward, Maple has a difficult time plotting the surface. And that can sometimes happen on some graphing software. Here's z equals the square root of 4 minus x squared minus y squared, again half of a sphere. And then lastly we have z equals e to the power of 1 minus x squared minus y squared. Let's go and determine some function values. Notice in order to evaluate this function we need both an x and a y value, which are both given. So we're going to replace x with negative 3 and y with 3 pi over 2. And now we'll just evaluate this. We're going to have negative 3 times the cosine of 3 pi over 2 is equal to 0, so this function value is 0. When x is negative 3 and y is 3 pi over 2, the z coordinate would be 0. For part B, we have x equals 2 and y equals pi over 3. So we'll have 2 times cosine pi over 3. Well, cosine pi over 3 is the same as cosine 60 degrees, so that's going to give us 1/2. Well, 2 times 1/2 would be equal to 1. So when x is 2 and y is pi over 3, the z coordinate would be 1. If we wanted to, we could write this as an ordered triple. It would look like this: 2 pi over 3, comma 1. And for number 2, it's a similar process. We'll basically perform substitution when x is 5 and y is 3. So we'll have 5 squared plus 3 divided by 3. So we're going to have 25 plus 3, it's 28 divided by 3. That doesn't simplify. And again, if we wanted to, the ordered triple would be 5, 3, 28 thirds. And let's go and take a look at one more, f of negative 4, 4. So we got to be careful with our signs here. We're going to square negative 4 and then add 4 divided by positive 4. So we're going to have positive 16 plus 4, that's 20, divided by 4, it's going to give us 5. So the ordered triple would be negative 4, 4, 5, which represents 1 point on this surface. Now let's talk about determining the domain of a function in terms of two variables. Well, if this function has two inputs, both x and y, all of the possible values of x and y will make up the domain. And the more that we can remember about our basic functions like y equals sine x, as we see here, and y equals cosine x, as we see here, will help us determine the domain of this function in two variables. What I mean by that is, for both of these functions down below, x can be any real number. So looking at this function here, x can be any real number, and so can y. So that tells us the domain is going to be all real numbers for both x and y. Let's go and take a look at another one. Here we have z equals the natural log of 1 minus x minus y. Now looking at this function here in two variables should remind us of the function in one variable of y equals natural log x. And if you remember, here's the graph. The domain of this function would be x greater than 0. And the reason that's helpful is if you take a look at the given function in two variables, the argument 1 minus x minus y must be greater than 0 for the same reason we have a domain of x is greater than 0 here. So again, the domain would be when 1 minus x minus y is greater than 0. Now this is the domain, but it's often better to manipulate this to make it look like a more familiar form. What I mean by that is we can move the x and the y term to the right side. So we would have 1 greater than x plus y. From here it's probably better to go ahead and switch this around to state that x plus y would be less than 1. And often when the domain is expressed in terms of two variables, it's helpful to graph this on the xy plane to show the region for the domain. Let's go ahead and do that. So x plus y less than 1 is going to be a dashed line with an x and y intercept of positive 1. And then if we test the origin, 0, 0 in this inequality, 0 less than 1 is true, therefore we shade this half of the plane. So any point in this region would be part of the domain of the given function in terms of two variables. Let's go and take a look at one more. Here we have z equals the square root of 4 minus x squared minus y squared. Looking at this, we should be reminded of the function y equals the square root of x when we have a function in terms of one variable. And again, we can see from this graph that the domain of this function would be when x is greater than or equal to 0. Remember, the square root of 0 is defined. So relating this domain to the given function, this should help us determine that 4 minus x squared minus y squared must be greater than or equal to 0. And that would be our domain. But normally it's not left in this form. Let's go ahead and move the x squared and y squared terms to the other side, and that would give us 4 greater than or equal to x squared plus y squared. And now we'll switch this around, meaning we have x squared plus y squared must be less than or equal to 4. And again, let's go ahead and graph this domain on the xy plane. Notice if we graphed x squared plus y squared equals 4, that would be a circle centered at the origin with a radius of 2. And since it can be less than or equal to 4, we'll make a solid circle. Again, if we test the point 0, 0, 0 is less than or equal to 4 is true. So for this problem, the domain would be all of the values on the circle or inside the circle. This graph represents the domain of the given function in two variables. Okay, that's going to do it for this introductory video. Thank you for watching.